Welcome, everyone. Can people hear me okay? Is this loud enough? Yeah, okay, great. Welcome to our Caltech Astronomy Stargazing Lecture. We have a great evening for you all tonight. Wonderful talk, and we've got clear weather outside, so hopefully the telescope observing should go well. I'm Dr. Cameron Hummels. I'll be your host for this evening, and just a few brief announcements before we get started. So the rough layout of the schedule for tonight is after I stop yammering in a couple of minutes, I'll introduce our speaker, and we'll have roughly a 30-minute presentation about the creation of elements inside of stars and in stellar explosions, which is super exciting topic. After that, we'll have a brief Q&A with all of you, probably like 3 or 4 or 5 questions from the audience. And then we'll kind of break, and there'll be telescopes that are being set up right now that you can go out and observe through. There's a number of astronomers out there looking at both the gibbous moon, which is really beautiful right now, as well as some deep sky objects like the Orion Nebula, a star-forming region nearby, the Whirlpool Galaxy. This is a beautiful grand design spiral that's face-on with us. A bunch of cool things through the telescopes. But at the same time as the telescopes going on out there, we'll have a Q&A panel going on in here, consisting of our speaker, myself, and another astronomer to answer your questions on whatever topics may come to you about astronomy or space science or physics. And so you can feel free to go back and forth between the two, check out the telescopes, come in and ask a question, or vice versa. And that'll go from roughly 8:45 until 9:45 when we'll start to clean up for the evening. As a reminder, these events take place about once a month on Friday nights. Our next one, I forget the exact date, but it'll be roughly a month from now on a Friday night, and feature actually a member of our audience right now, Professor Monsi Kosliwal, who has a child making some noise. And she's going to talk about a really interesting explosion that takes place on a type of star called a nova. You've probably heard of supernovae. Yeah, the child's not a big fan of the nova. You've probably heard of supernovae, but there are also types of stars called novae that are a different phenomena. And this one had a brightening because of an explosion that took place about 80 years ago, and we've now predicted that it's going to happen again in the next few months. It'll brighten in the sky to about the same brightness as the North Star, whereas now it's much fainter. But it's always exciting when you can predict something about the future and then it happens. So she's going to talk all about the phenomena of these novae objects. In addition to our lectures that take place in here, I guess I should just say we're coming up on our 100th lecture in the next couple of months, and I haven't procured the speaker, but it's going to be good. It's going to be good. I'm going to ask like Kip Thorne and Andrea Ghez, so it might be a Nobel laureate, which would be pretty sweet. So stay tuned. I will have that announcement as soon as I figure out who it's going to be. But in addition to these events, we have a series of events that take place in a bar in Old Town, Pasadena called Astronomy on Tap. Those take place at an outdoor beer garden. They're all ages, so family and children are welcome to come. They just can't drink beer. And these feature 2 20-minute or so informal presentations by local scientists, both from Caltech or NASA Jet Propulsion Laboratory or UCLA or the Griffith Observatory, and talking about science, much like this, but it's less formal because it's in a beer garden. There's astronomy-themed pub trivia. There's live music. It's super fun. We also have telescopes there, but the telescopes here are better because of the darker conditions on the field. And the next one of those will be a week from this coming Monday, April 29th. And it'll feature a scientist from JPL, Joe Lazio, who's going to be talking about technosignatures, which is to say looking for signs of extraterrestrial civilizations that have higher levels of technology across the galaxy or across the universe. And there's also going to be a talk by Professor Smadar Naus, who's from UCLA, talking about gravitational wave sources in the centers of galaxies. So it should be a really, really fun evening. And I guess, what's that? Oh, you're unhappy that I'm talking too much? Oh, fun. Oh, I thought it was like, come on. I was like, oh, geez. Get booed here. Huh? I must ask: did people get an opportunity to watch the solar eclipse last week, either here in Pasadena or perhaps along the center line? Good. I'm glad people had that opportunity. We had an event on the field just behind us. We had like a few thousand people who showed up, which was super cool. And then there were a number of us who went and put on public education events in on the Texas-Mexico border on the path of totality, and had a few thousand people who came out to that, which was awesome. So stay tuned. 2026 and 2027 are the next solar eclipses that you'll be able to see. They'll be in Mexico, Iceland, not Mexico, forgive me, Spain, Iceland, and Northern Africa, like Egypt and Tunisia. So it should be pretty sweet. The next ones that will be visible from North America and the continental United States aren't until 2044 and 2045. So you've got a long time to wait unless you travel to see a total solar eclipse. Okay, enough of my rambling. I would like to introduce our speaker for tonight. Our speaker grew up in New Jersey, in northern New Jersey, and did her undergraduate studies in physics and astronomy at University of Maryland, where she finished a number of years ago, and then joined the department here as a PhD candidate in the Department of Astronomy, and has been doing some really amazing research with the professor who just walked out because of the child outburst, involving what are known as astronomical transients. These are just short-lived kind of flashes or week-long events, much longer than normal timescales in astronomy, that can be observed with a number of new telescopes or new instruments aboard telescopes that are around here, like at Mount Palomar or the Keck telescopes. And oftentimes these involve stars and the explosions of stars and the collisions of stars. And she's going to share all of that with us tonight. So. And she's defending her PhD in about 1 month. So we will soon be able to call her doctor. So we'll call her proto-doctor, because she's soon going to be a doctor. Shreya Anand, please welcome.
Thank you so much, Cameron, for having me, and thanks everyone for joining for this talk. So I'm going to talk to you today about cosmic gold mining. And I'll start with this quote from Carl Sagan, which is, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." So what does that actually mean, we are made of star stuff? It turns out that this is quite literally true. The elements in the human body have astrophysical origins. So for example, hydrogen, helium, and lithium were produced in the Big Bang. So you can see the hydrogen in our bodies, which comprise 10% of our bodies, were produced actually in the primordial cosmic explosion. Elements such as carbon, which are the essential building blocks of life, were actually formed inside the cores of stars. And other elements that are essential for DNA formation, such as phosphorus, potassium, sulfur, sodium, magnesium, these were produced in the depths of massive stars once they explode as a supernova. And so quite literally, we are made of star stuff. And it's really amazing to think about this. So I'm sure that most of you have seen this periodic table of elements in your chemistry classes, probably in high school, maybe a long time ago. This is the way that astronomers think about periodic tables. So you can see that the lighter elements, hydrogen, helium, lithium, were formed in the Big Bang. Other elements were formed in exploding massive stars, exploding white dwarfs, cosmic ray fission, and dying low-mass stars. But today I'm going to tell you about the heaviest elements in this periodic table. The elements you can see here that are marked in orange. And these include rare metals, rare heavy elements, such as uranium, europium, platinum, and gold. So gold is actually something I've had a fascination with from when I was pretty young. Actually, in our culture, I come from South India. In our or my family comes from South India, I should say. In our culture, gold is considered very rare and very precious, and also very sacred. And so you can see people from infancy to old age wearing articles of gold. Many of us in this room are probably also wearing some gold ring after getting married. So turns out California also has an interesting history with gold. Between 1848 and 1855, 300,000 people traveled to California for what is known as the California Gold Rush. And gold was actually discovered just north of LA. This is a picture of mining on the America River in Sacramento during the California Gold Rush around 1850. And 750,000 pounds of gold were actually found in California during that time period. So where does this gold actually come from, and why is it considered so precious? So first, let's talk about how this gold is actually made. Yeah, go ahead. Oh, yes, I'm blocking this. Okay. One moment, sorry. Maybe I'll pause. You got it? Okay, thank you. All right. Thanks a lot, Cameron. So let's talk about how this gold is made. So we know that heavy elements, including gold, are made through the rapid neutron capture process. And in order to understand this process, we should first go through the slow neutron capture process. So here what happens is that you have a heavy seed nucleus that captures a neutron. So here you can see, suppose we have a heavy seed nucleus of silver, Ag, here. And here you can see atomic number as a function of the isotope number, or the number of neutrons. And so we start with silver. One second. No worries. Just trying to figure out where the mouse is. There we go. Okay. Yes. That worked. Yes. So heavy seed nucleus captures a neutron and then undergoes beta decay, or it releases, in other words, it releases an electron and forms a heavier element, cadmium. And similarly, this process continues. So with this nucleus of cadmium, it goes on capturing these neutrons and then undergoes another beta decay to form a successively heavier element. So in this way, through the S process, or the slow neutron capture process, you can form heavier and heavier elements. This occurs over time scales of millions of years. And this is known to produce some of the lighter elements in the periodic table. Now, imagine this entire process on steroids. That is the rapid neutron capture process. So here you have heavy seed, you have a very dense environment rich with free neutrons and very heavy seed nuclei that rapidly capture several neutrons so quickly that the nucleus does not have time to undergo beta decay. And so you quickly form these unstable neutron-heavy nuclei, and eventually you beta decay to form very heavy elements. And this occurs over time scales of seconds. So you can imagine that a process that essentially occurred over time scales of millions of years, if that has to occur over time scales of seconds, then you need really extreme energetic environments to facilitate this process to occur. So what are the cosmic laboratories in which this rapid neutron capture process can occur, or this R process? Two main sites have been proposed. The first site is neutron star mergers, and the second site has been collapsar supernovae. And I'll hopefully by the end of this talk, you will go away knowing what both of these sites are. These are both extremely energetic explosions that occur in space, enabling this violent our process or rapid neutron capture process to occur. So let's talk a little bit about what these explosions are. Neutron stars and supernovae are both linked to massive stellar death. So if you have a massive star that is 8 times the mass, more than 8 times the mass of our sun, it will continue fusing elements. And this fusion process is what actually powers the powers the star and continues its life. So eventually when it runs out of fuel, it can no longer burn, then it will expand as a red supergiant. It will puff up. I'm sure many of you are familiar with Betelgeuse. So have you seen Betelgeuse? Yeah, so Betelgeuse, the red supergiant. And so this is an example of an evolved star. And once it reaches a certain point, it will shed. It can no longer support itself. So it will shed its outer layers violently in a supernova explosion, leaving an extremely dense core behind. And it can either leave behind a neutron star, which is the extremely dense core of a massive star, or it would collapse on itself, forming a black hole. So these black holes and neutron stars are actually stellar corpses. So, as I mentioned, neutron star mergers. Neutron stars are actually very extreme objects, very dense objects. Imagine the mass of the entire sun packed into a 10-kilometer radius. Yeah, so that's probably the densest object that you can imagine. And this is a neutron star over LA County. So this is how, imagine if there was a neutron star above LA County, this is what it would look like. So these are very rare objects. And you can see that they're extremely dense. But a single neutron star is not enough for our process production to occur. The key is that you need 2 neutron stars. And having 2 neutron stars in a binary system is what enables the process to occur, because you actually need to break the neutron stars in order to get a dense enough environment rich with free neutrons for this rapid neutron capture process to occur. And so theories many people have theorized how this process can occur in neutron star mergers. So what you're looking at is 2 neutron star mergers, which eventually attract each other. They inspiral in and eventually merge. And when they merge, they create this violent explosion. First, as they are merging, they distort space-time. And so they create ripples through space-time that are detectable through gravitational wave detectors. I'm not going to talk about gravitational wave detectors now, but feel free to ask me questions after the talk. And so these 2 neutron stars will inspiral in and merge to form a black hole. And from that black hole launches an extremely energetic burst of gamma radiation or gamma rays. And this gamma ray burst will collide into the surrounding medium, forming an afterglow, which is detectable in the optical and infrared bands. And in addition, as I mentioned, the merger of these 2 neutron stars results in this R process. And the R process is detectable in what we call as a kilonova. So this is an optical and near-infrared signature of the radioactive decay of heavy elements. Maybe you'll understand it better when I show you this video. So hopefully this video will work. Let's see. Okay. So on August 17th, 2017, a very spectacular event occurred which revolutionized the field that I work in. And this is called GW 170817. And just as theories predicted, we were able to observe a cataclysmic event in which heavy elements were actually created. So here you can see the two neutron stars which are spiraling towards each other. They are creating gravitational radiation, gravitational waves, which are ripples in space-time. And as they spin in towards each other closer and closer, they merge and they form this burst of gamma radiation. And this, maybe this is going probably a little too quickly for, let's see, maybe we can play this once more. There we go. Yeah. So once again, this in spiral gravitational radiation, you can see them coming closer and closer together. And eventually, as they merge, they form this jet. You can see this jet. And then here in the center, that is the depiction of the formation of heavy elements like gold, platinum, lanthanides, and actinides. So this is a really prolific event that revolutionized our field. And in fact, this is the very first time and the only time that we have observed direct evidence of the production of heavy elements in these cosmic explosions. So you can see that they're also extremely rare events. So I'd like you to focus on this panel here. It might be a little bit hard to see, but let's see. Can you see my cursor? Okay. So this is the galaxy NGC 4993, which is 40 megaparsecs away, or about 100 million light years away. And in this galaxy, if you keep looking at this spot here, you can see something up here. It's very blue initially, and slowly it evolves. The color changes over time, and it becomes redder and redder. It might be hard to see this in the back, so I'm just narrating. And this blue to red color evolution, the way the color changes over time, is actually indicative of the production of these heavy elements. So this is one of the signatures of heavy element production. And you can see that these are transient events, meaning that they do not have constant brightness, but they have brightness that evolves with time. So you can see that at the beginning, it starts out very bright and slowly fades, or should I say rapidly fades. If you look at this time axis, you can see that it is over the course of just 10 days that this source starts from extremely bright and then fades to nothing. And now I'd like you to look at this figure here. So this is showing brightness as a function of wavelength, what we call as spectra. So we take the light from an object, we put it through a grating and split it into various wavelengths so that we can study the individual elements that are produced in the explosion. And you can see here that, again, let's see. We'll just wait for this to start from the beginning. But you can see that as it starts out, it's very hot, it's very bright. And eventually it fades. But as it fades, you can see these particular lines, these features coming out of the spectrum. And these broad features are signatures of individual heavy elements that are contributing to the light in this kilonova. And so you can quite literally see the elements that are produced in GW 170817. So we are striking gold in this event. So what do other fields have to say about the production of these heavy elements like gold? We can take some clues from what is known as galactic archaeology, or study of the history of the galaxy and other galaxies, and also geochemistry, the chemistry of the Earth, in order to understand more about the astrophysical sites in which these heavy elements were produced. And so here you can see a plot which shows the rate of events, of such events in the Milky Way, and the mass of our process or heavy elements that are produced in each explosion. And we have clues from various types of studies, including detection of plutonium-244 in the bed of the deep sea. There were deposits found of plutonium. Plutonium is a very heavy element produced in these, well, we think it's produced in these neutron star mergers. And so that gives us one of these curves here, right, which constrains how many events occurred and how much was produced per event. Similarly, there were uranium detections in meteorites, which were studied actually by some professors at Caltech. And that also gives us some constraints in this two-dimensional space. And finally, detections of the heavy element europium in dwarf galaxies, which are very small galaxies, much smaller than our Milky Way, give us a curve here. So saying that the rate of events in the Milky Way and the mass produced per event is constrained to this portion of the space. And so we compare that to the detection of GW 170817, which for which we have a rate estimate, and we also have an estimate of how much mass, how much our process mass in solar masses was produced in the explosion. We can see that it actually matches up pretty well. And so that's a really good indicator. So neutron star mergers can actually explain the heavy elements that we see in our solar neighborhood and in the universe, as far as we know, the total amount of heavy elements. So yes, and roughly, to get us the idea of scale, 10,000 Earth masses of heavy elements are produced in each of these explosions. Okay, so now I'm going to talk a little bit about a different, slightly different type of astrophysical site. For the very first time in 2020, neutron star black hole mergers were detected. So if you remember earlier, black holes, hold on, yes, black holes and neutron stars both originate from the death of very massive stars. So they're the remnants of these supernova explosions. And so it turns out that these neutron stars and black holes are also attracted to each other. And in a similar fashion, they find each other, they're attracted, they inspiral towards each other and merge. And so this is what this simulation is showing here. And because you also have a neutron star that could be potentially ripped apart, you have similar conditions that can be conducive for the production of our process. And so it turns out that all neutron star black hole mergers are not expected to produce our process that is detectable to us. Here, you can see that the size of the black hole actually matters. So if you have a black hole that's about 3 times the mass of the neutron star, up to 5 times the mass of the neutron star, then you can tear apart the neutron star. So you have a process known as tidal disruption. So here you can see this neutron star, which is being tidally deformed from its spherical shape. It's being pulled by the black hole. And eventually, you can see it's tidally ripped and forms this accretion disk around the black hole. It forms a disk around the black hole. However, if the black hole is too large, then the neutron star will actually be swallowed whole. And so you don't get any light from this explosion. This is a dark explosion. So that's why the title is black or gold. So it really depends on how the mass of the black hole compares to the mass of the neutron star. So far, we have never observed light from one of these systems, but we are keenly interested in searching for kilonovae, or the light emission, from these neutron star black hole mergers and from these binary neutron star mergers. Yeah, I see the light has been, I don't know what happened. Thanks. Thank you. All right. So how do we actually find these things? I work with the Palomar Observatory. Palomar Observatory is located just about just a few hours south of here. It's okay. Thanks, Cameron. Yes. And you can see that Palomar Observatory has a variety of instruments that are very well suited for finding these the sites of our process. And so it has this, the Palomar 60-inch, which performs robotic imaging and spectroscopy of bright sources. It has Palomar 48-inch telescope, known as the Zwicky Transient Facility, which is a wide field robotic imaging survey of the entire northern sky. Here's a picture of me. It's hard to see this, but it's a picture of me standing next to ZTF. And this ZTF is our primary discovery engine. So this is what we use for discovering various transient phenomena, which are what Cameron talked about a little bit earlier. And then we have this large 200-inch telescope, which performs follow-up spectroscopy and imaging of very faint sources. And so we can use this to study more deeply the sources that we discover with the Zwicky Transient Facility. So how do we actually search for the next neutron star, binary neutron star merger, or neutron star black hole merger? So first we get gravitational waves from the neutron star merger, if you remember from the video. And this gravitational wave signal is then sent to us in a way that we can automatically ingest this into our database. And so we have a dedicated database that will be able to tell us immediately when a gravitational wave from a neutron star merger occurs. And this database has the ability to phone call us. So you put in our phone numbers, and sometimes in the middle of the night, we get a phone call, it wakes us up. Or even during the day, it can happen anytime. And once it happens, then we decide, okay, so are we going to search for the light emission from this gravitational wave source or not? And so we have many different, we have a lot of different information from the gravitational wave merger that helps us decide, for example, whether the event is actually observable from our telescope or not, or whether it's perhaps not interesting because it could be a terrestrial event that happened due to noise on Earth. And so we decide whether or not we will trigger or whether or not we will observe with our telescopes. And finally, when we decide to observe, then we get various different transients, so phenomena that vary over time, that fade over timescales of days. And we can look at them in our database and decide whether those look similar to the event that I showed you earlier, GW170817. Do they look similar? Do they look different? Do we really think that these are potential kilonovae? Finally, we can get imaging and spectra, and then disseminate the results to the public. Okay, so now we come back full circle, and we can say that merging neutron stars are actually responsible for this, for many of these heavy elements that are shown, or basically all of the heavy elements that are shown here in the periodic table. So are we done? We know that neutron star mergers produce the heaviest elements in the universe. We just need to find more of them, right? Not quite, I would say. So there are some potential issues with assuming that neutron star mergers may be the only site of heavy element production. So first plot that I'm showing here is the solar R process abundance. So this is the measure of heavy elements in our solar neighborhood or in our solar system. And it follows this particular pattern. So this is as a function of the atomic number. And you can see that it has this very distinct pattern to it. So we don't know whether these neutron star mergers actually reproduce this pattern. We've only seen one event so far. So we need to see a lot more of them in order to understand whether they can actually reproduce all of the heavy elements that we see in our solar neighborhood. And secondly, there are some other mysteries, which are that these tiny galaxies that I talked about, the dwarf galaxies, actually show that they were enriched very early in their history. And the problem is neutron star mergers are formed as a result of stellar death. So it happens over timescales of, it happens over extremely long timescales. And not only that, but these neutron star mergers occur because two neutron stars find each other and eventually in spiral and merge. So there's a delay time associated with the formation of a neutron star and the merger of these neutron stars. And so it takes a very long time. So how can we explain the enrichment of very old, tiny galaxies with these neutron star mergers? So one potential alternative is collapsing massive stars, which could be an alternative site of heavy element production. These are very massive stars, greater than 30 times the mass of our sun, which collapse in on themselves after spinning very, very rapidly to form a black hole. And these are also, since these are also very energetic phenomena and extreme phenomena, there have been simulations that are run that show that heavy elements could be produced in these explosions. So, yeah, and they also produce an associated supernova. The good thing is we have the ability to detect these supernovae with the instruments, with the telescopes that we have at hand, and specifically with the Zwicky Transient facility, we are able to see several hundreds of thousands of these over the course of a few years. So overall, I think we have detected about 10,000 supernovae with one of the surveys that we conduct with the Zwicky Transient facility. So we're able to find these sites of heavy element production. And so let me skip this video. So as a part of my thesis, I've also been looking at these massive star supernovae to see if these could also be sites of gold production. And here you can see a diagram showing other elements produced in the supernova, along with the heavy elements that are produced in the core of the supernova explosion, and how much the heavy elements mix with other elements determines whether or not we are able to detect the signatures of the heavy element production. So here you can see this is the brightness as a function of time. And if the inner and outer layers have a lot of mixing, then we're able to see very red signatures. If you remember previously from the kilonova I showed, GW170817, how it evolved from very blue to extremely red due to the heavy element production. In a similar way, we expect that these supernovae will become very red in their observed colors due to heavy element production. And so if we see a lot of mixing between these layers, then we'll be able to detect the heavy element production in these supernovae. And so as a part of my thesis, I looked at these supernovae. Unfortunately, we did not find any robust signatures of heavy element production, but that doesn't mean we should stop looking. I think we should keep looking and look in a more systematic way. All right, so just to conclude here, where are we now? So what do we know about heavy element production in the universe? We know that binary neutron star mergers can produce the heaviest elements that we see around us. We struck gold once with GW170817, and we believe that every single binary neutron star merger actually produces these heavy elements in the periodic table. Neutron star black hole mergers are another potential site. We have never seen light from these events, and they could be black or gold, depending on whether the neutron star is swallowed whole or whether it's ripped apart by the black hole. And finally, collapsar supernovae are a big open question. Although they are routinely observed, they are very frequently observed with wide field surveys like ZTF, we still don't know whether they actually can produce these heavy elements. We've never seen it before. And there are some other potential sites of heavy element nucleosynthesis. So stay tuned for more news on this as the field progresses. Thanks very much.
Okay, now we'll take a handful of questions from all of you. Question here in the front.
So many people would be surprised to learn that the total amount of gold that's been mined, like in the history of human civilization, would fit in like an Olympic-sized swimming pool. So it's not a lot of gold that we've found on the Earth so far. So my question is, do we have any idea from observations, whether it be of other bodies in the solar system, planets or moons or exoplanets, or even from stars or these mergers? I know you talked about the one where we had the direct observation. Do you have any idea whether like the distribution of gold on the Earth is typical of what we would see in other bodies in the solar system or in the universe, or whether there's a abnormally high or low amount of gold, just given the size of the Earth and the relatively very small volume of gold that we've found on it so far?
Yeah, that's a really good question. So I don't know that well, there have been no studies of, like, for example, other planets for us to get an idea of how much gold deposit, whether the gold deposit that we have on Earth is representative of what could be found on other planets. But what we do know is that, I guess, so for some of these studies of dwarf galaxies, for example, you can see relatively high enrichment in the individual stars. And dwarf galaxies, these tiny galaxies, which are metal poor or they don't have a lot of heavy elements by themselves, are actually really good laboratories for understanding more about these astrophysical sites. And so they provide a very clean environment, which helps us trace back the history of heavy element production. So for example, one could study there have been studies of the europium deposits in these stars, which indicate that there was one event. So like one neutron star merger that is responsible for enriching these stars. But I don't know whether the amount of gold deposited on Earth, for example, is actually representative of other environments, I guess, especially outside the galaxy. Yeah. Mm-hmm.
So I'm interested in the triggers that you have for determining whether an observation is worth looking at.
Yeah.
So I guess like the best way to ask this is, envision it's like 1 a.m. and you get a notification that there is a merger or a gravitational wave detection happening.
Yeah.
Could you describe like the ideal night that was going to make you stay up and investigate? Like, what is the scenario? What are the conditions that'll make it something worth chasing?
Yeah. So one thing I didn't really mention in the talk was that the gravitational wave detectors, which are on and constantly detecting these signals throughout the day and night, these can detect signals from binary black hole mergers, which I didn't mention, these binary neutron star mergers, neutron star black hole mergers, and also has a lot of contamination from terrestrial events, so just noise sources in the detector. And there's a way of quantifying whether or not we believe that the source is astrophysical and what the classification of the source is. So we would look very closely at, first of all, we want the source to be very, high probability of being astrophysical. And secondly, we would want it to be, well, the ideal event would be a binary neutron star merger, because we believe that every single one of these produces heavy elements. And also for neutron star black hole merger, we would get excited. We'd probably, if that happened now, we would probably trigger ZTF. Mansi's there smiling. And yeah, it turns out that actually, as we speak, the LIGO detectors are on and detecting these mergers, and anytime now it could detect a neutron star merger. Yeah.
So you'd run out in the middle of the presentation.
Yeah, exactly.
We have to observe this right now.
Absolutely.
A couple additional questions from the audience.
So you talked a lot about like the R process for creating heavy metals. For the S process, does it have to have any like certain special conditions for it to happen, or does it just happen like all the time?
That's a good question. So here, the S process is actually, the S process contributes to all of these elements shown here in yellow or in gold. And so basically you still require these heavy seed nuclei to be present, which is possible in these dying low mass stars. Yeah, so you do require specific conditions in order for S process to also occur. Yeah.
Actually, this slide actually kind of answered the question that I was going to ask, because it's cut off at 92, but I was going to ask with the heavier elements that I know we make in particle accelerators, some of them only exist for thousandths of a second. And so I was going to ask if the merger is enough to create those elements. Can you, like in that GIF that we saw that was 10 days long, would you be able to see the spectra like change as like really short half-life heavy elements decay over that range? Or does it, are the elements that it's creating in this merger like sufficiently stable that you don't see like half-life taking place over the time of observation?
Yeah, that's a really good question. I think it would be hard to detect elements that have such a short half-life. So
is there like an upper bound for atomic number that it would create from these then? Or is that 92 like
I think this is correct. That I think it's up to 92.
Oh, okay.
I'm not completely
yeah.
I know that some elements are only created like in human laboratories. Yeah. But I think in practice we would only be able to detect the elements that, or the decay products, I guess. not the, yeah. So, sorry, merger of neutron star and black hole. So we don't actually expect the merger of black holes to create heavy elements. We don't even know if they produce any light at all. There are only certain specific conditions that may allow for light production from these binary black hole mergers, but for the most part, we don't expect them to be. So if anything, it would be these neutron star mergers that we would be able to see these heavy elements from. Yeah.
All right, we will take more questions after the break for our Q&A panel, but let's thank our wonderful speaker, Shreya Anand. Okay, so the conditions were a bit hazy out there, but we've got 3 telescopes set up. I encourage you to check them out, but we're also, in about 5 minutes, we're going to set up a table and do the Q&A panel in here for the next hour. So you can go out and check it out, come back in, stick around, go out later. There's usually a mad rush for the telescopes, and then you inevitably have to stand in line anyway. So you could just stick around. But yeah, we'll get started. We'll have a brief intermission while we get set up and start our Q&A panel in about 5 minutes. And way to handle that was a chunk. I don't know if there's plutonium lines that you can see. I mean, maybe.
I don't know.
I don't know. Yeah.
No idea.
It's a good question.
It's a really good question.
Okay.
So,
I have a question for you. I understand there's a gap time gap between the arrival of gravitational waves and light waves, even though they both travel at the speed of light. But I understand this is certain, yeah, it's like very short. So how can you have decision making about, oh, should we look through the telescope or not? Because that's very short warning. Unless you get the gravitational wave and you miss the first part of the wave front of the light, and maybe start looking at our
yeah, so basically the delay is, yeah, what you are referring to is the gamma ray. So that typically for gamma ray detectors, they will be they are very widely used. They have sensitivity to a large portion of this current, and so they can immediately react.
So you don't have to make any decision.
So there's no decision making in battery because they know that it could be exactly the same. But yeah. And there's expected time. So we think that.
What you say there's only a 2-second time.
So that's for the gamma rays.
Okay. And
So gamma rays are, but then we expect that there's some time for the light to become optically. So then we basically allow for this thing of optical IR, like expect that there's about half a day to a day.
I see. It's that long.
Yeah.
I see.
Let's.
So that's it. If there's still merit in if we have as quickly as possible. Because the only thing one is that you don't really know.
But you can see the oh, gamma rays are very
Yeah.
optical telescope that.
Of course. So if we have gamma rays,
No.
yeah.
Gravitation.
Yeah, so the problem is that we have so many contaminated sources. So we can't, and actually this I didn't say triggers are very different. So normally with the DTM, for example, we are conducting a night research. So we have the and if we want to trigger the telescope every time we get that, then it won't disrupt the so there will be very selective to look at only the things that
And even your decision making has to be quite fast. Is it
Still has
important or not?
It still has to be. So usually written in half an hour to an hour. But that's how much, unfortunately, we need to have that much delay because yeah, just the process of looking at the event, making the decision, triggering it, getting it started.
And often you might be mistaken. So
Exactly.
it's important.
And it's yeah, it happens. Yeah.
Okay, great. Thank you.
All right. Welcome back from our brief intermission. We'll get started with our Q&A panel. So I'll just have each of us introduce ourselves and give a brief introduction to what sort of science we work on. We're happy to take questions on whatever you want to ask about. We can't promise to know the answer, but we can potentially work out the answers depending. We each have different focuses. So I'm Cameron Hummels. I'm a research staff here. I primarily do computational modeling of galaxies and cosmological structures in big supercomputing simulations, and then use the outputs of those simulations to make predictions to what our telescope should be able to see, both for galaxies as well as the atmospheres around galaxies or the distribution of galaxies. It's basically like all about galaxies for me. But yeah, so that's mostly what I work on.
So yeah, I did introduce myself, and Cameron introduced me quite sufficiently. But yes, I work on transients in general. So phenomena that evolve over time scales of days, and whose brightness decreases over time. And I study these with the Zwicky transient facility, which I mentioned in the talk.
Hi, everyone. My name is Naveen. I'm also a final year PhD candidate, joined between Columbia University and now Caltech now. I am interested in all aspects of high energy astrophysics and also transient phenomena. I study them using using computational simulations that we run on supercomputers of plasma physics around what are called compact objects, the black holes and neutron stars, because the plasma physics around these objects is extreme, and they give rise to these highly energetic phenomena that we see. And sometimes I also study them by directly observing using satellite-based telescopes, X-ray telescopes, and gamma ray telescopes. Yeah.
Excellent. Okay, so now we open it up to all of you. I can see a hand already.
Yeah, can you explain a little bit more about the R process? For example, does it make sense to talk about half-life of beta decay? And suppose, for example, a neutron is free floating and happily going about. Will it actually spontaneously decay into a proton and an electron? And why is it faster in those extreme situations you talked about in your talk?
Okay, I can try to answer that one. So a little more about the R process. So you have, as I mentioned, there are these heavy seed nuclei, which then capture the neutrons at a rate that is so fast that it's unable to undergo beta decay in the same way that the slow neutron capture process occurs. And so, so you basically form these very unstable nuclei and then rapidly form these heavy elements. So the reason for neutron star mergers, for example, being an ideal cosmic laboratory for this process to occur is because there are basically that environment is very rich with free neutrons, and because you have these two neutron stars which are breaking, you have this the breaking of the neutron star crust due to the merger. You're basically squeezing the nuclei together and enabling this process to occur over a much quicker time scale. I don't know if that answers your question somewhat.
Roughly address what you were asking? Yeah. I have a question.
Can you explain more when you had the graphic with the R process and you had the images of the molecules and the neutrons being captured? On the third of those images, it looked like there was one additional proton. So is it implied that whether it be something that happens with the neutron that's captured or the loss of the electron, that is what does it create an additional proton? Because the number of protons is what would signify that it's a heavier element, right? Like that we distinguish between, right? So what is happening to create that additional proton? Is it the loss of the electron? Is it something that happens to the neutron independently that makes it positively charged and makes it a proton?
Great question.
Yeah, so it would be the loss of the electron, so undergoing beta decay that forms the heavier element.
Trying to think of a good color for a neutron.
Yeah.
What do you think? Blue? Blue can be a neutron?
Sure. Yeah, maybe Calvin can.
So this is, sorry,
Go ahead.
I find illustrations to be very helpful. So a neutron is, by its name, it's neutral, and you can effectively create one by combining a proton and an electron together, because a proton has a positive charge, is pretty bulky relative to the electron. The electron has negative charge, doesn't have a lot. And if you combine them together, then you form a nice neutral guy. So, oh man, colors. Here's our electron with a negative charge. Here's our neutron. Looks kind of like an N. And then here's our proton with a positive charge. So if you combine these together, then you can make that, or vice versa, as the gentleman was asking. Neutrons are intrinsically unstable elements that over time will decay into a proton and an electron. I don't remember the time scale. Do you guys remember the half-life of a neutron decay? It's pretty long. Oh, no, 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 no. I mean, just a neutron, just a naked neutron hanging out will decay, but I think it's a really long time scale. I'm sure people online right now who are watching this are looking it up. What you know off the top of your head? How does it remain stable within a nucleus? So when a neutron is part of a nucleus, it's much more stable. It's only when it's just hanging out by itself. It's like, I'm not so happy out here. And then it shoots out an electron and it becomes a proton. But when it's in a nucleus, and I don't know enough about particle physics, to know exactly if we understand why, but when it's in a nucleus, it's much more stable and it can hang out kind of indefinitely. So I don't know. I didn't mean to steal the show. I just like illustrations. Yeah. So yeah, you're flinging these neutrons into a heavy nucleus, and they're shooting out these electrons in that beta decay. And as they're shooting out the electrons, they're converting the neutrons that are present into protons, which is increasing the atomic number of the element. So it's turning from silver to cadmium to, I don't know, what's after cadmium. Do you remember all these different?
No.
Okay. Yeah. I memorized part of the periodic table, but not that part. So yeah, does that? Okay. Sure. Yeah, that makes sense. Does that roughly cover the explicit? Okay. Okay, cool. There was a question in the back.
There was some mention of gold, which is a very precious metal on planet Earth. What will this be used your studies, or how is it related to this lecture this evening? Let's say maybe 30 years from now.
Sorry, just to clarify, what your question is, how does the study of gold deposits on Earth relate to this study? Or could you?
Sure.
Yes. Okay. So it goes back to the plot I showed with the rate of these events as a function of the amount that is being produced by each event. And so studies of deposits of gold and other heavy elements on Earth can help actually constrain how many such events occurred in our history of the solar system, for example, and how much mass of heavy elements in solar masses were produced per event. So I mentioned the example of the deep sea plutonium deposits. So they have precise measurements of how much plutonium was deposited. And then based on that, they sort of extrapolate a little bit and say that based on the amounts of trace plutonium that we see in the deep sea, we can go back and say that this much mass of heavy elements in total was produced by some explosion, some neutron star merger, probably, that occurred in the history of the solar system. Yeah. Does that answer your question? Somewhat. Oh, in the future?
So in the future, will the gold content of the solar system change in the future, or is that what you're asking? Or what will our knowledge of? I don't know I don't understand what your question is. Like, how the value of gold will change over time? Okay.
Is it how studies of gold now will affect our understanding in the future?
Yeah, we can discuss in detail about that later.
Yeah, we can. Yeah. I'm happy to talk to you. Later. Yeah.
There was a related question. I think it was rhetorical, of how we can get the pans into space to pan for gold in space, which of course is kind of ridiculous. However, there are efforts to potentially capture asteroids that may have a much higher content of certain precious metals like gold or like silicon or these sorts of things, and mine those extraterrestrial sources and bring back the stuff. It's a ways off, I think, as has been demonstrated by recent studies like the what was the mission that Osiris, but also what was the one that we slammed into the DART? Yes, the DART mission. Like we're at the beginning of being able to impact other asteroids and change their trajectories and be able to do this sort of thing, but it's a bit of a ways off. It's a hard problem.
Landing the spacecraft on an asteroid, it's an extremely hard problem because it doesn't have a very strong gravitational pull either. So one has to maneuver the craft so precisely to be able to go and affix itself onto asteroid surface. So yeah, it's hard.
Indeed. Okay.
So maybe this is for you, Cameron. So, our sun, right, is creating hydrogen and helium, right? Is that right? It's not created, or has a lot of it. So it's relatively stable and kind of small mass, relatively speaking. So there's a lot of stuff in our solar system. Do we have any thoughts on like where that stuff came from? Because it's created someplace else, right?
So this is.
So are you referring to other elements that are created in the solar, or that we see in the solar system?
Yeah, I mean, so our sun didn't create what's floating around our sun, right? It vacuumed it all in, and so do you have any thoughts on what else is the bodies that are out there or what's relatively close that might have created all the stuff that is
part of our solar system, our planet, ourselves, our sun? Sure.
Yeah, so this is again going back to the history of our solar system, like these explosions that occurred way before the solar system, or before the solar system formed, and then the formation of the solar system, these elements were incorporated, and also into the similarly in the Earth, right? And so we believe that supernovae occurred in the history. So the explosion of massive stars. We believe that neutron star mergers, well, at least a neutron star merger occurred in the history of our solar system, in order for these elements to be present here now, for us to be detecting them on Earth and in the solar neighborhood. So yeah, we expect that many other types of explosive phenomena occurred in the history of, or previously before the solar system formed.
That's absolutely right. But the one thing I'd add, just to give it full context, all the material that makes up us, that makes up the solar system, at its base was formed during the Big Bang, at the beginning of the universe. And it's just been enriched with heavier elements from processes like what Shreya was describing, from earlier generations of stars. They took some of that hydrogen, some of that helium that was created during the Big Bang. They formed a star and then produced heavier elements in the core of the star or in these collisions of objects. And so you slowly end up enriching that material with not just hydrogen and helium, but some of these heavier elements, or carbon or nitrogen or oxygen, in the same way that cool periodic table slide that she showed the different elements and where they were generally produced, whether it's low mass dying stars or if it's these binary neutron star mergers. And then we're just, our sun, there's pretty good evidence that our entire solar system, the planets and the sun, formed about 4.6 billion years ago. And that formed from the leftovers of previous generations of stars that exploded or fizzled out or whatever. And then we were produced from these very elements that came from those cores of stars.
There's no relic of that supernova.
The relic is the stuff that it left behind, but we can't see like a continuing shock wave. It was too long ago. For instance, when we look up in the night sky, we can see certain objects they might be able to see the Crab Nebula tonight. It's up, but it might be in the haze. But this is the remnant of a supernova that exploded about 1,000 years ago. And you can still see it kind of expanding because it's only been 1,000 years. And thus, that will continue to expand, dissipate its material into the surrounding area. And then any stars that form, 1,000, a million, a billion years later from that stuff will incorporate those elements into that generation of planets and stars. And that's what it is for us too. We can't still see like the shockwave from 5 billion years ago of the stuff of the binary neutron star that occurred that eventually, provided us with material. But
that's one thing. And the other thing being the stars and the compact objects like neutron stars and black holes that are formed inside of the supernova remnants, they also receive a kick when they are born. So they even before the supernova remnant diffuses into the surrounding medium, even before it becomes tenuous, the stars that are formed inside of it, they receive some kick velocity, some natal kick velocity, and that can impart enough velocity to these objects that they get out of these supernova remnants at some point in time. And moreover, these objects also they sort of rotate around the galactic center. So there are many opportunities for these objects to escape out of the supernova remnant given sufficient time. So you won't see the relics after billions of years.
Yeah. Great question.
How close to two neutron stars have to be before they start actually interacting with each other? Like, is it because the closest star we have is like 4 light years away? So when does the interaction start? Is it like one stronger than the other? When does it start to pull, or when is it actually interacting with each other? Yeah.
How close do you have to get before they're going to actually coalesce?
Yeah, that's a good question. And the distance that has to be the minimum distance that we want between two neutron stars in order for one of them to be ripped apart is comparable to the size of a neutron star. So if this is a neutron star and this is another neutron star, the distance between them has to be somewhat like this, comparable to one neutron star radius. And only at such closer distances would the tidal influence of the companion star be strong enough to rip material off of the neutron star surface and start producing the R process elements and everything. If they are, say, a few neutron star radii apart, they would be still, they would start becoming tidally locked. For example, the Earth and Moon are tidally locked, right? We just see one face of the same side of the Moon. But if you put Earth and Moon a bit farther away, the Moon would be able to rotate independently, and we'll see all faces of the Moon. So you just have to bring these neutron stars up to 1 or 2 neutron star radii, and then they'll be tidally locked, and then you'll start ripping material off of their surface. That's how close they have to be.
But it's hard, right? Because most of space is space, right? So the likelihood that you get 2 of these stars so close together that they're like, this close is usually pretty uncommon. And so there aren't a lot of these events that occur relative to just
more than early stage of the universe that you see them come back together than there are today.
Not really.
The question.
A really good question. So you're imagining the universe to be extremely small at earlier times. So all these stars are packed together, and so that's your imagination, which is intuitive, which makes sense. But that's not true, because at earlier times you would not have formed neutron stars. It takes a really long time to form neutrons. It takes hundreds of millions of years after the birth of a massive star to form a neutron star. So the way to bring 2 neutron stars together right now is through gravitational radiation that Shreya mentioned. So when you put these 2 systems together, they have some orbital energy to them, right? So they orbit each other, they have some orbital energy. And if you extract this orbital energy off of the system, they will come closer to each other. And how do you extract this energy? Through gravitational waves. So these neutron stars, they emit gravitational waves and they lose their orbital energy, thereby coming closer and closer. That's how you bring them together, and it takes a long time. Yeah.
Before there are a handful of questions from the YouTube audience, and I just wanted to ask one that's related to this, and that is, what prevented the rapid neutron capture process forming heavier elements during, like, shortly after the Big Bang itself, when again, it's a much denser environment, there's a lot of stuff flying around. Why wouldn't you form heavier elements? Because right now, most of the elements that were formed in that initial explosion of the Big Bang were hydrogen, helium, and a little bit of like lithium and maybe beryllium, the third and fourth elements. But why didn't we form more during that period?
Yeah, so it goes back to what Naveen said in the last question, which is that you actually, like, this process of forming the neutron stars and then getting them to inspiral and merge occurs over much longer timescales, which would not have been possible in the early universe when you don't have not sufficient time has passed for these early stars to have evolved and then undergone a supernova, left behind a remnant, and then these remnants finding each other over 100 million year timescales and inspiraling and merging. So basically, you need to budget enough time for this entire process to have occurred for the heaviest elements to form. So that's why we don't see this in the early universe.
That's certainly true for like the stellar bombardment of neutrons, but even like before stars even formed during the Big Bang, there would be a lot of particles around, but I just don't think it lasted long enough at those high densities to allow fusion from beyond helium to heavier elements, because everything's expanding really, really quick. And so it expands, I think it expands just too quickly to boost up to higher and heavier elements.
Some other kinds of fusion occurred, right? Probably fusion of quarks or something occurred to form neutrons in the first place.
In the first place, yes.
In the first place. So probably some sort of fusion did occur, but it just did not, there just was not sufficient time for the fused products to fuse again.
That's right. I think that's the general idea. I promised this gentleman, but then, we'll get to everybody, I promise. Thank you.
Thanks so far for the insights. I have two questions regarding the black hole neutron fusion. And the first one probably relatively simple. In theory, when the neutron star gets swallowed, do you still think it produces elements or only when it gets ripped apart? The second question, and bear with me because I have nothing to do with physics or astronomy, but I'm just wondering, why is it 3 to 5 masses of a neutron star? Because in theory, I'm thinking, well, if it's more than one, it should be enough to fit in there. So is there like a volume discrepancy where like a black hole is, even if it has the same mass or 2 times the mass, it's so small that a neutron star physically can't fit in there? Like, why is it at 5?
Okay. First question first.
Yes. Yeah, these are both great questions. So, okay. So the first question was about, sorry, can you remind me the first question is about the... Oh, yes. Yeah. So the short answer is no. We don't really expect heavy elements to be formed when the neutron star is swallowed whole and when the black hole is large enough. The second question...
Is it just because like the thing that allows these heavier elements is the presence of all these neutrons? And if you have 2 neutron stars, then you've got neutron sources from both. But with a black hole, there's only neutrons from the neutron star, right? So it's not...
Right, exactly.
It's not getting pummeled with all of these neutrons that are boosting up the elements, or else the neutrons are just flying into the black hole and then they're like, they fall into the black hole.
Yeah. Well, so when it gets ripped apart, it's forming heavy elements through 2 different processes. So one is, well, I guess primarily it's forming it through the tidal disruption, which occurs during the merging process. And so as the So we expect the final remnant to be a black hole, right? From the merger of a neutron star and a black hole, you'll find the final remnant to be a black hole. But the material that's being ripped apart is going to allow for this R process to still occur.
Basically, the force of that destruction will emit heavy elements into space before.
Yeah, I don't know if they'll escape or not. They might just fall into the black hole along with the rest of it. And then at which point you're like, oh, there's more gold, but it's inside the black hole. So like, what can you do?
So it depends if you have a black. So I guess the closer the mass of the black hole is to the mass of the neutron star, the more likely you are to see a bright signature from this, or the more likely you are to have matter remaining outside the black hole. So it's essentially the matter that remains outside the black hole that we can detect. If it's falling into the black hole, we're not able to detect it on shorter timescales. And then to your second question, which is regarding this sweet spot of 3 to 5 solar masses. So it's not. So actually, it's somewhat simpler. When I gave the talk, I sort of simplified this in a way. So it also depends on the radius of the neutron star and the spin of the black hole. So if you have very high black hole spins, you can also get that changes the radius of the innermost stable circular orbit. So how do I explain this? So maybe
about the innermost stable circular orbit, right? So so you have a black hole, and you have to send a neutron star closer to a black hole in order to rip it apart, right?
Yeah.
So
maybe if you draw it.
Black makes a good color.
Yeah. So let's assume a black hole of some mass, and I'm going to draw a sphere around it. Let's call the tidal disruption sphere. Okay. So whenever you put a neutron star within this sphere, it's ripped apart. The radius or the size of this is determined by the mass of the black hole. If you increase the mass of the black hole, this increases. This R increases as the mass of the black hole to the 1/3. So you increase the mass of the black hole by 8 times, okay? Then this radius increases by 2 times. It increases very slowly. So at some point, the tidal radius, but the size of the black hole, it's gm over r square. So the size of the black hole increases as mass. So if you increase the size of if you increase the mass of the black hole by 2 times, the size increases by 2 times. So at some point, as you increase the mass of the black hole beyond, say, 5 solar mass that Shreya mentioned, the black hole will be larger than the tidal disruption radius. So if you throw a neutron star towards a black hole, the tidal disruption radius, the new tidal disruption radius is somewhere over here, which is inside the black hole. So the neutron star has to go inside the black hole to be ripped apart. So once it gets inside the black hole, you're not going to emit any substance outside it. So that's the 5 solar mass threshold that Shreya mentioned. So once you increase the mass of the black hole, basically the disruption radius gets inside of the black hole, so you won't be able to disrupt a neutron star at all anymore. And smaller black holes mean the disruption radius is outside of the black hole. So you just put something outside of the black hole, it rips it apart already. So
and things like the radius of the neutron star and the spin of the black hole can also change.
Yeah, that also affects
these where the radius of ISCO, which is what he was talking about, the dotted line, where that is placed relative to the size of the black hole.
Next questions. Yes. Okay.
Thank you. Was there a supernova explosion or something like that preceding the formation of the supermassive black hole in the center of our galaxy? And if so, did the resultant wave of debris then create the rest of our galaxy?
Interesting. So we don't, I'm just going to jump in here, but feel free, we can converse about this. We don't think that the supermassive black hole in the center of our galaxy formed in the same way in which stellar mass black holes, these ones that are 3, 4, 5 times the mass of our sun, formed. And that we actually don't have a really good answer for how these really massive ones in the centers of galaxies form. So the one in the center of our galaxy, I think it's 4 million solar masses. But we see these supermassive black holes in the centers of galaxies anywhere from a few 100,000 times the mass of our sun to billions of times the mass of our sun, dependent on the mass of that galaxy itself and kind of the history of stuff getting into it. And we see evidence for these really massive ones, supermassive black holes, in galaxies across the universe when the universe was, the light that's reaching us is from the universe when it was quite young as well. And it is not well understood what the formation mechanism of those supermassive black holes are at such an early stage in the evolution of those galaxies in the universe. But it's a very active field of research. It's possible that it could leave behind remnants of material around it, depending on what that formation mechanism was. But I don't know. Do you guys want to? You do compact objects, so maybe you have some insight on this.
No. I think Cameron addressed it. We definitely do not understand the formation of supermassive black holes. Some of the most massive stars that we know of are hundreds solar mass, 100, 200 solar mass. And if they explode and collapse, the most massive black holes that you can form immediately off of these systems is few tenths of solar mass, 30 solar mass, 40 solar mass, and so on. And there is some gap, and then you can produce few tenths of solar mass. One way to produce such humongous black holes is not through stellar explosions, but perhaps by hierarchically merging smaller black holes. So you bring together two black holes, they merge, you form 200 solar mass black holes, and then you continuously start merging these black holes. That's one way of producing much heavier black holes. Another way is for these black holes to accrete matter. So you put a black hole and then put a star next to it. It pulls off material from the companion star, it accretes matter, and then it grows. And these are just some ways for a black hole to increase its mass, but still how it reaches a billion solar mass is still unsolved question.
Because those processes take a long time.
Exactly, they take a long time.
And the ones that we've observed in the early universe had to have formed in a very short period relatively speaking, like 100 million years or a couple 100 million years. And if they were to form by like, I pull in this material and I pull in this material, it would take a much, much, much longer time scale. So people are looking into ways that perhaps you could have, a very large structure like a proto-galaxy that consists of millions of solar masses of material that could somehow collapse and form this all in a single event, as opposed to slowly building up over time. Because otherwise I don't know how you do it. It's a hard problem.
Perhaps the same way that a accretion disk in our solar system came together and the dense part. Sorry. So perhaps in a way like the accretion disk that formed our solar system came together in the center, became more massive, and then became our sun. On a much larger scale, on a galaxy scale, the same thing happens, only the material that accretes in the middle forms a massive black hole rather than something stellar.
Possible. It's possible. It's not, like I said, if we had the answer, we'd be famous. But yeah, it's a possibility that you could have this massive gravitational collapse on a galactic scale that might result in something like that. It's possible. Yeah, good question. Oh man, so many questions. This gentleman has.
So there was a question earlier about trying to detect heavier elements with shorter decays. Kind of on a more philosophical side, how do you, as scientists, grapple with the gap between what you can measure with instrumentation and what you think is actually happening out there? Is that the kind of thing that keeps you up at night, or do you feel confident in your measurements?
Yeah, this is I mean, definitely it's something that keeps us, well, at least speaking for myself, keeps me up at night.
I stay up a lot
Yeah.
thinking about the limits and sensitivity of our instruments.
Yes, for sure. So I guess one example of this in related to what I was discussing regarding our process is it's actually, I made it sound like it was much easier than it is to understand what elements are formed in the spectra by taking spectra of these events. So both of the neutron star mergers, but also of massive star supernovae. So the collapsing massive star supernovae. There's a lot of complications because there are a high density of lines that are produced due to the heavy element production. So it's kind of, so you need very detailed modeling of these events, whether they be kilonovae or supernovae, in order to understand what elements are produced. And sometimes different models can there can be conflicts between different models as to, at this wavelength, what line do we expect? It's not very clear cut sometimes. For example, on the other hand, for core collapse supernovae, there are some specific elemental signatures that we know pretty well where those lines are expected to occur, and when we measure them, we see the lines, and it matches up. Theory matches with observation. We can identify what elements are produced. For example, this is true of hydrogen in in specific types of supernovae. We can identify the hydrogen signature pretty robustly. But then when it comes to these very heavy elements, there's often debate about whether we're looking at the right lines. So yeah, definitely it's an issue. I don't have a good answer for how we solve this, but yeah.
Make better instruments that have more precision, or yeah.
Sure.
It's definitely a challenge though. Oh boy. Oh man. Okay. I'll get you later because you've already asked a question. You've already asked a question. Don't worry, we'll get to you, but you haven't.
No, thank you. This is hopefully very simple. For your periodic table, the colors weren't shown uniformly. Why was that? Like in the heavier elements, it'd be like mostly orange and a little yellow, or they'd be more even,
Yeah, that's a great question. So it boils down to what processes we believe can produce these elements. And so there are some elements, there are few elements on the periodic table which are purely one color. So those would be considered to be pure art process elements. But then some other elements, as you mentioned, could be produced both via the S process and the R process, or via different, like, other processes. Some elements can be produced within supernovae, but they're also produced in massive stars in stellar fusion. So it boils down to having multiple ways to produce a particular element.
Was it like a quantified percentage? Like if there was a small bit of yellow, but it's a small percentage produced?
Yeah, so that's,
like,
yeah.
Is it quantifiable how you've determined that, or is it theoretical? So just like a thought.
Yeah. So yeah, to some extent it is quantifiable. I don't know with what precision we can say this for, especially the heavier elements in the periodic table. But in the periodic table that I showed, yes, so a smaller percentage. If the box has a smaller amount of a particular color, that means that it's mostly produced by a particular process and less by a different process. Yeah.
Questions?
My question is about geochemistry, because somebody was talking about the amount of gold on the surface. And the surface, let's say, to a depth of a mile or something like that. But I would imagine that when the Earth was a molten ball, then all the heavy metals, elements would sink to what is now the core. And therefore, just looking at the surface gives you a very bad estimate of how much of each element is produced. So you probably want to look at astronomical objects which are already in a very hot state rather than sampling the Earth's surface. Is that correct?
Yeah, absolutely.
The reason why surface was emphasized there was because if you take elements like plutonium, the Earth does not produce plutonium in its core, and neither does Sun produce plutonium. But if we have plutonium, it's through external source. And if we are capturing these heavy elements from an external source, and if you are looking at Earth right now, there's no way for plutonium to sink into the core, rather just stay in the surface, and because it's captured from external source. And that's the reason why a surface level identification of heavy elements is preferable rather than digging down into the core, because
yes. So in the early history of the formation of the solar system, absolutely, you'll have these planets will be molten and hot, and you'll get differentiation of heavier elements that will preferentially sink to the core, and the more lighter elements are more buoyant and will sit on the surface. So you do get this, but today, obviously, we don't have that same sort of fluid, viscous, convective flow that it would allow for this differentiation to occur.
Yeah, but I guess also what you said about looking at other sources, or looking at not in geochemistry, but perhaps galactic archaeology and other sources to understand more about heavy metal production is definitely correct. I would say I mentioned earlier, I keep coming back to these dwarf galaxies. Or there's another example, which is the stars in our galactic halo, which are known to be metal poor or have mostly light elements. And so we expect that if there was an R process event that occurred, then it would provide a very clean environment for us to measure that R process deposit in those stars. So specifically, studies take spectra of these individual stars in the galactic halo and then measure the abundances of heavy elements found in these galactic halo stars. So they look for on the surface. Yes. Yeah. On the surface. Yeah, that's right. Yeah, correct. So they would look for these pure R process elements, as pure as possible. Things like europium, which is known to be, I believe, fully or almost completely attributed to the R process.
I just wanted to address a really quick question from the online audience. Is a collapsar the same as a type 2 supernova explosion, or is there some difference?
Yeah, there is a difference between the collapsars and type 2. So collapsars are, collapsar comes from collapsing massive star. And these stars are much more massive than this. Well, we believe they're much more massive than the stars that produce type 2p supernovae. So about 30 times the mass of the sun. And these stars are rapidly rotating. And so when they collapse, they immediately form a black hole. We believe type 2p could also will primarily leave behind a neutron star remnant. And these collapsars also are linked to long gamma ray bursts. It's another thing I didn't really have time to mention in the talk. And so they collapse in on themselves, form a black hole, and the material around the black hole gets circularized into an accretion disk around the black hole, enabling also the launching of a relativistic jet, which is observable in the form of gamma ray burst or gamma rays. So yeah, there are a lot of differences, I would say.
Cool. Okay, that's great. All right, there's a gentleman in the back.
So coming in today, I was aware of the environment in which the heavier elements were created, but today is my first time learning of the mechanism behind it. So I have two fundamental questions behind the mechanism itself. So first is the slow process. I noticed that, like the gentleman over there asked, how I think it was up until bismuth that it was decreasing. Is that due to like a fundamental cap in energy available, or is it just that when you mentioned it takes a longer time, it just hasn't had enough time in the life of the universe to actually create these higher elements? And second, this is just counter to my intuition, the beta decay. How does losing an electron lead to a heavier element? So those two questions. Thank you.
So the thing that I poorly drew there is when you spit out an electron, it's like you're spitting out a -1. So what's left is a +1. So you're converting neutrons into protons, which boosts the atomic number. It boosts the number of the element. Yes. Because the nucleus has both protons and neutrons in it. It spits out an electron from one of those neutrons, converting that neutron into a proton, which keeps the same atomic mass, but it increases the atomic number by 1. So it moves up that way.
Changes in the properties of these elements is determined by not the number of neutrons in an atom, but by the number of protons in an atom. So you can have two atoms with the same number of neutrons, same mass, but if you just change the number of protons, they'll have very distinct properties. They'll have distinct color and so on. So it's when you say gold and so on, you're talking about the number of protons and not the number of neutrons.
And when you're adding additional neutrons, then you form heavier and heavier isotopes of a particular element. And to your first question, I believe there is a fundamental cap on how heavy of elements you can produce, you can create via the slow neutron capture process. And beyond that, you need the R process essentially to produce these elements. So if you remember, I guess going back to that periodic table, you'll see some of the elements will have contributions from both S and R process. But then as you get heavier and heavier, for example, uranium, which is 92, I think. Yeah. So uranium is considered to be just produced via the R process. So there's a fundamental cap.
Yeah, it's a tug of war between how fast an atom can decompose in some sense versus how fast it accumulates matter. Yeah, so if you accumulate matter faster than the rate at which it decomposes, it grows in mass. But even if it grows in mass, that does not guarantee that this atom will stay stable. So there are these islands of stability. So somewhere between atomic mass of so and so, if one atom reaches this mass, it can stay stable. So you stop the accumulation of neutrons on top of it, it will not decay, it will stay stable. But once it starts adding some more mass by adding neutrons, it is out of this island of stability, so it can decay very fast. So it's hopping between these islands of stability by adding more and more neutrons at a much faster rate than the rate at which they can decay. So S process, as Shreya rightly mentioned, cannot produce heavier elements because it's very slowly accumulating neutrons, and after some point it starts decaying. So the decay rate is quicker, so it can't grow any further.
So in theory, if a heavier element was more stable, it could skip one, right?
If a heavier element were, oh, if you didn't have these islands of stability, if it was just stable across.
Or n plus 1 is not stable, but n plus 2 is stable. It would skip n plus 1, but still be able to
so it wouldn't really skip n plus 1. It would just live in the n plus 1 mass for a short time. So an atom has 100 grams of mass. So 110 is unstable, 120 is stable. Once it reaches 110, unless you keep on adding mass, it's going to fall down back to 100. You keep. Yeah.
Yeah, good questions. Okay. Running out of time here. We got to get to all the questions.
All right. So you mentioned that the plutonium has been naturally discovered. Has the same been done for neptunium, technicium, or promethium?
I don't think so.
Yeah, not that I know. Is this on? Okay, yeah, not that I know of.
And their half-lives are extremely short, I guess.
Yeah.
So plutonium can live for several tens and hundreds of thousands of years, but these unobtainium, like 10 plus elements, they have extremely short lifetimes. So I don't think they have been discovered in nature.
Yeah.
Wild.
In fact, come to our Astronomy on Tap about looking for signatures of advanced civilizations, because one such technosignature that there might be this advanced civilization is the presence of something like technicium, which would have too short of a half-life to occur naturally that we'd be able to observe it. So if you see it, you're like, oh, something's amiss, something's weird. Maybe they're artificially creating this long enough that we can observe it. I wanted to get this one last question from the online audience. So it might sound like a silly question, but how did all these heavy elements that we were talking about before find their way to planets after they were produced by supernova and neutron star mergers? And it's related to what we were talking about, you know, but I figured it'd be worthwhile just to talk about like the planet and star formation process. And that's just that you've got a bunch of gas and dust and stuff that's undergoing its own gravitational collapse, and it starts to collapse usually into a bunch of stars kind of simultaneously. In fact, I don't think they were looking at the Orion Nebula, but the Orion Nebula in the night sky is a good example of a nearby star forming region that's undergoing this very process. And when these individual stars start to collapse, or the gas is collapsing and getting denser and denser, and eventually in the cores, you have the formation of stars, you have nuclear fusion processes that halt that collapse. And usually you have planets that are forming around kind of in situ in this disk, as was alluded to by some of our previous questions, in the disk around that star. And that's how we believe that all the planets in our own solar system are orbiting in this same plane, is because they all formed at roughly the same time as our star was forming. So the fact that the stuff from those earlier supernovae or whatever ends up into the planets, that's like you started with You started with gas and it eventually formed into the stars and the planets. That's just that's where it went. That's where it ended up. It's not that it got pulled in later or something like that. Okay, well, second question from Brian Federa.
It's actually good that you circle back to this because it's apropos of this. So the gentleman had asked the question earlier about relics, and you were talked earlier, and you talked more explicitly now about the objects in the solar system forming out of a cloud of gas and dust, or they collapse and condense and so forth. What I wanted to say earlier was that we can't see that process here because it's already happened billions of years ago, but we actually have observed it elsewhere in the universe. So we have images of these clouds forming around other stars. So if that's the kind of relic, kind of that you had in mind of that like intermediate stage between just a cloud of gas and then the finished product of a solar system, like you can find images from our space telescopes of that. So.
That's right. Yes, that's a very good point. That's a good point. Intermediary steps in the evolution of these systems. I'm going to get a question back here.
So this might be a basic question. So what's the difference between a supernova, hypernova, and a kilonova? And do stuff only from supernova like create all these metals, or does the other thing also create these metals?
So many nova.
Yes. Well, we should probably start with a nova. What is a nova? So a star like our sun will eventually undergo, when it runs out of fuel to burn in its core, which powers it, which makes it bright, it'll eventually undergo a nova and produce a very dense, compact object known as a white dwarf. So that's a nova. And supernova, you can imagine this on, well, supernova occurs for stars that are much more massive than our sun. Stars that will be fusing elements up to carbon in their core and eventually collapse into a dense remnant, which is called a neutron star. And then it sheds its outer layers in an explosion called as a supernova. So that's what a supernova is. A kilonova is, well, it was initially termed that way because it was supposed to be 1,000 times brighter than a stellar nova. So like the ones that we would expect our sun to go through. But it turns out to be a misnomer in many ways. So it's, so kilonova is occurring when the cores of these, so when after a supernova occurs, so star much more massive than our sun, explodes and sheds its outer layers. It forms a neutron star, and neutron stars are actually attracted to each other gravitationally. So they will find each other eventually in spiral and merge. And that merging produces another violent explosion in which these heavy elements are created. And so we call that explosion as a kilonova. Okay. And the hypernova was the last one. So hypernova, is another, it's another word for the collapsar supernovae, which I mentioned earlier. So this would be stars that are 30 times the mass, at least 30 times the mass of our sun, rapidly rotating, they collapse into each other. I mean, they collapse into themselves, forming a black hole, and then they launch a very fast relativistic jet. And so this phenomenon, well, I guess, the associated supernova that occurs as a result of collapse of this massive star is known as hypernova. So a very, very bright, energetic supernova. Yeah.
Just to add to that, the other difference between these three classes is that in supernovae and hypernovae, majority of the emission is through thermal emission. It's through heating up of the material that is ejected off of these supernova or hypernova. Whereas in kilonova, the brightness is primarily due to the radioactive decay of heavy elements. So you decay these heavy elements, they produce electrons through beta decay and also some photons, and it's the photons that are created due to this decay process that's powering the kilonova, whereas in supernova and hypernova, it's mostly heating up of. You also have nickel decay, which contributes to the decay of the element nickel, which contributes to a significant portion of the overall light curve, but it's mostly thermalizing or heating up the substance directly through collision and neutrino emission from the cores that is powering the supernova and hypernova, unlike kilonova.
Okay, so thanks for sticking around. Sadly, it is 10 o'clock already. So this brings us to the end of our Q&A panel. Please, let's thank our speaker and our panelists. Excellent job, guys. And as I mentioned, we will have an Astronomy on Tap in a week and a half on Monday, April 29th at the Dog House Beer Garden in Old Town, Pasadena, featuring a couple of really interesting talks on gravitational waves and signatures of potential extraterrestrial civilizations across the galaxy and the universe, astronomy-themed pub trivia and music. And our next one of these, I don't remember the exact date, but I'll put up the poster in the next few days, will be the middle of May. It's already May. So thanks again for joining us. We'll see you guys next month. Have a wonderful evening. It was great.